Ma'am's mic is not working.
So many hiccups. It is really. Yeah. So after this second summer of AI, we again got this second winter of. So then it came the oh no, in this network thing, I have lost my base, like where I am, either I'm in the winter or I'm in the summer. So the second AI winter, right, the second winter was cut out uh, when the expert system actually proved too expensive to maintain, and they were criticized a lot, right? So because they were rule-based system and it was very difficult to keep them in order, right? So the new diseases, the new symptoms are coming, and how to keep them trained. And at that time, the general purpose computers from Apple and IBM also were started solving more real world problems. And then the AI systems, again, but they were very expensive systems. So by 1991, Japan's fifth generation computer project actually finished, and after 10 years, and it could not, after spending $400 million, it could not meet even one of the objective they decided. So, but what happens as you can see that the thing is working here. Okay. So as you can see, just a minute. No, I will come through there only. So by 2011, then the Apple releases its virtual assistant Siri, we all know, on iOS, and then it actually brought AI closer to consumers, and that is how after that time we didn't stop. Let me come over there. That would be. So when I tell then how this era of deep learning starts, so it actually, if you go back, so in 2012, then this experiment is being done. So the Google's Mysterious X Lab, they actually tried to mimic human brain, and they simulated their experiment on the neural network of 16,000 processors with 1 billion connections. And when they let it browse YouTube videos, thumbnails, basically for 3 days, then you can imagine what happened. Their algorithm, they actually started looking for the cats. So what happened? More than 75% approximately cat, then 80s, more than 80% about human body parts. That is what. And what was told by the team director then that they didn't tell anything about the what sort of data, what sort of videos are there. Actually, that program started learning towards, right? Learning things from those video itself. So after that, so I will take a couple of examples and then we will move away. So this is a AlphaGo. So this is a board game. And then what happened in 2015? Actually, this Google's AlphaGo AI wins the 3 match series against the world's top Go player. And that was again a remarkable change in the field of AI. And people thought that yes, some promises it can fulfill. And so it followed, and this is one of my favorite example, which I used to give in the class, that dermatologist level classification of the skin cancer. So in 2017, if you look at the page, this picture, this research was published, which was done by a group at the Stanford University, and they actually did it for the skin lesion images. So if you talk about the skin lesion, then it is one of the common cause there, and the texture is there, which is supposed to be analyzed. And what they did is that they pre-trained their deep neural network at general object recognition, then they fine-tuned it around 130,000 skin lesion images and more than 2,000 diseases. And the most remarkable point was that they have shown they have tested their model. The performance of their model was tested against 20, I'm missing the number, 17 or 21, right? Board certified dermatologists, and the model beats them all in not only in the simple cases but also the complicated cases of the cancer. So this is one example when the people have started thinking about that it can fulfill the promises. You can see this. This is nothing but inception V3. I hope we will cover it up in one of the class. So what when we talk about the deep learning, then what is the difference in the approaches of the 2 decades, right? 1997 to 2017, because in there when this IBM chess computer that beat the Gary Kasparov in 1997, that was explicitly programmed to win, right? But what was the difference here when we talk about AlphaGo? AlphaGo was not pre-programmed to play the Go game, right? So it is actually learning the thing by using the general purpose algorithm, which is allowed to interpret the game's pattern. Now, so AlphaGo program actually applied deep learning, right? Now with this, you can see that nowadays deep learning is being used everywhere, whether it is internet or like you can see so many application classification, language translation, language processing, sentiment analysis, whatnot, right? Then medicine and biology, like I'm also working in the area of medical image analysis. So we are working on, we worked on the mammograms, we worked on the brain tumors, brain MRIs basically. Then recently we are working on the fundus images and how to dive the retinopathy from the fundus image, right? So those type of then entertainment all it is there. You all I mean knowing more than me. Then security and defense, of course, face detection, satellite imagery. So you can see, and then that driverless car, right? So many of my young minds, right? They want that car to be with them, right? Parked at their home. So you can see that actually deep learning has brought AI into the forefront. Okay? So artificial intelligence now has penetrated every aspect of your life. So what is deep learning basically? A machine, this is nothing but a machine learning technique, which actually allows computer to learn and improve its performance by learn experience and data. Now, also, how this gets power? Basically, it represents the work as a nested hierarchy of concepts, not in a one go. I mean, slightly, right? So, slide by slide, some features, then low level, then high, middle level, high level, like that. So, it is building a hierarchy of concepts, and each concept is actually defined in terms of the simpler concepts. So, you can say that we are defining more abstract representation computed in terms of less abstract representation, right? So here you can see that this is a typical deep learning architecture. So you can see that, okay, there is a training data. Using this training data, you are training your algorithm, and once your model is trained, then you are using this model for prediction, and you are giving this unseen data, and your model predicts it, right? So here you can see that machine learning, what we do, basically we are providing computer the ability to automatically learn without being explicitly programmed. So we are giving like a child, right? You are giving examples, and by those examples, my model is learning. So I'm not telling it explicitly what programming is there. And so, but when we talk about machine learning, at that time, features are learning, right? We are relying on the feature because the model based on the data, the machine learning algorithm extracts the features, and based on those feature matching, right? It is going to give you results. Now, so as I told you that because I'm a computer vision person, so I have given you all example related to images. Shift is one of Shift, HOD. These are the very I mean famous features in computer vision. So, but what are the limitations of the traditional machine learning algorithm? See, we call it curse of dimensionality. Suppose you have the same dimension of data, right? With the same data, if you are increasing that feature dimension, then what happens that initially the performance increases, but then it stops, right? Then it may decrease also. So this is called basically a curse of dimensionality. When the number of dimension is very high, then it's initially it gives you good, but later on it decreases performance. So this is called peaking phenomenon. And so when we talk about machine learning, what is the thing? Basically, we are having this handcrafted feature extractor. Then we have trainable system and the output. So here you can see that this manually designed features, because I gave you shift, I gave you HOD. So every time I tell about teach my students shift, and every time I wonder like how this feature has been evolved. This is wonderful, right? If you study over there. So, but the manual features which are there, they are often over specified, they are incomplete, and they are mostly application dependent. So the literature, pattern recognition literature, if you go on machine learning, it is full of features, right? So every time a new research, new paper is coming, which is giving us a new feature which is working good in this new application, right? So it is so this handcrafted features, it is time consuming to design and validation these machine learning systems, and therefore we can say that it is a costly as well as complex. Now, if we come to the deep learning, then deep learning learns rich hierarchical representation automatically, right? So it is, we are not telling it what to learn, it is learning automatically by extracting features at different levels, right? So you can see here picture, first of all, low level features, mid level features, high level features, and that is how it is learning through a hierarchy. So deep learning actually provides you a very flexible learning framework. And so here you can, your trained algorithm will work for a broad range of problems. Now, so here you can see that as the same picture, now the different picture is there. So you can see that right from the pixel to the classifier, okay? So each layer here, each layer, so first layer, second layer, third layer, what do you mean by these layers? That will be clear very soon. So each layer of the hierarchy extract features from output of the previous layer, right? And also that these layers are having nearly similar architecture, and the good point is what? That we are training all the layers jointly. It's not like that first you are training first layer, then second, then third, but you are training all these layers jointly. And that is how you can see that your first layer learning edges, second layer learning object parts, and third layer may be your objects. So this is what is your, what do we mean by learning a hierarchy of feature extractors in deep. So now if we compare machine learning and deep learning, so we can say that the traditional machine learning flow, it's a manual feature extraction, plus you can say selection. So you are selecting after feature extraction, you want to perform the feature selection, the good features you want to keep, and then classify, but such shallow structure is there. And as I told you, what are the limitations? That is the issue with the handcrafted features as well as the curse of dimensionality. Now, in place of this deep learning, deep learning is nothing but end-to-end learning. Remember, I told you from pixel to object classifier, right? All layers are being trained jointly. So we can say that, and here we will get, in fact, you can, so that is what is the difference between the machine learning and deep learning flow. Now, so what is the, when we say that the deep learning is so much successful that is why we all are studying it and we want to use it in different aspects. So what is the success mantra for deep learning? Basically, how it is possible today, which was not possible there, that is the increased availability of data, right? Then second thing is significant improvement in the computing power, then increased model size, and auto feature extraction. So here you can see that the deep neural network architecture, we are generalizing them so that they are flexible to address a broad range of problems. So what happens, this, the professor was introducing you the ImageNet. So ImageNet is a huge image data set, and this has come with the on the initiative of Professor Lee from Stanford University. So what happened when she started research? Then she was working on the medical image analysis, and she found that the good data is not there. So at the like, if you just hear some of the TED talk of her, you'll find that at the time when other researchers were working on the machine features, right, machine learning algorithms and finding out the more and better and better features, she put finding the good data, collecting the good data for training. And so in the initial years, there were no results. And then finally, like that data set, actually, so this whole thing that we'll tell you in the, when I will tell you about CNN, is that it started in 2012 when your first deep learning model came to beat the traditional models, right? Traditional machine learning based models. So if we consider the hierarchy of the advancement over there, so like NVIDIA, so CUDA processors, right? Then GPUs came, then democratized data access began, and you can see so much, right? So many TPU finally, this is same as some of the things told you to you by Professor Beek. So we can say that democratization of AI knowledge, computing power, new tools came, right? Keras, PyTorch, you are going to learn also. Then, so AI service has started. So because of this AI, these advancement happen with the deep learning. So when we talk about deep learning ingredients, the first ingredient is the ANN, artificial neural network, which is a learning machine. Then the data, algorithm to train artificial neural networks, and of course the computing resources. Right? So these are the ingredients of the deep learning, you can say. So this portion somehow I'm going to revise you. So ANN, they are based on the concept of a perceptron. And so perceptron are nothing but an information processing paradigm which is inspired by the human brain's information processing mechanism. So you can say that it is composed of large number of highly interconnected processing elements which we call neurons in our brain, and they work in unison together to give you solution for a problem. So ANNs are learning by example like humans learn. So perceptron, as you know now, that they are the fundamental building block of the neural deep learning. And so here you can see this age of the perceptron, right? So first Rosenblatt, he gave it in 1957. After that, we learned Minsky-Papert report was shown to you, and then it started then in 86 when the because I mean as here you can see the multi-layer perceptrons, but we don't know how to train them unless and until we know about the backpropagation algorithm. So after backpropagation algorithm, then the in 2010 the age of deep network started. So then we are having the algorithms, computing power, big data, everything which is required, every ingredient which is required to give you the solution. So inspiration, as you can see, biological neural network. So this is the picture I have taken from the slide of Professor Vic. So here you can see that very basic level in the brain we are having neurons, right? So what is the main purpose? Main purpose of neurons is to receive, analyze, and transmit the information in a form of signal, which we call as the electric pulses. And when a neuron sends information, we say that it is being fired. Okay. So what happens? A neuron receives information, sends information to, you can say, there are thousands of neurons, they are interconnected with each other, and that is how the information flow goes on. So we can say that acting through here, you can see a specialized projection known as dendroids. So here you can see that specialized projection known as dendroids and axons. So here you can see that they carry information throughout this neural network. So inputs are combined, and when they exceed a threshold, then we say that then actually the neuron sends a spike. So that which travels through this axon to the other neuron, right? So that is how it works. And so this is again the here the slide from Professor Vic, that this is, you can say that these are the inputs and these are the weights we are giving to the input, and this weighted sum when we are applying this activation function over there, and that is how you are going to get the activation, or you can say output. Now, if we call about this new mathematical model, so you can see that this is my biological neuron and this is my model. So what you can see that in the model, you can see from axons, you are getting the signal. So this these various inputs, right? Different weights are given to these inputs. They are being added together, multiplied and added together. Then we are applying activation function, and that is how you are going to get the output. Now, always remember that these neural networks are loosely inspired by the biology. They are not the exact model how your brain is working. Just we have taken them as a inspiration. So this is your perceptron, and what is happening here? If you consider, this is nothing but a sequence of labeled examples, and these are weights. Then you are getting the weighted sum, and the typical function which was used as an activation function in the perceptron model given by Rosenblatt, that was a sine function. So either like you can say this is a binary, you can say unit step function. So if now here you can see that why I am using this activation here. So see here, weighted sum and then this activation. Why this activation function is required? Why this activation is required? Non-linearity. So what happens that if you consider the real world thing, right? They are non-linear in nature. But if you look at this here, this is a weighted sum, which is a linear operation. So just to add the non-linearity here, the sign function is going to be added, and that is how it is giving me output, right? So this is your perceptron algorithm. So you can see that initially, let us say randomly you are initializing. Let us say I am saying okay 0. You are initializing it. This is your input. Input, let us say for simplicity, we are taking just a binary vector. And then so what is our target? Our target is to find some weights, right? So that you are going to have this weighted sum and you are going to get the value of output, right? Which is going to give by this perceptron. So if you look at there, then it seems just a one-line code. So what does one-line code does? Just see this working over there. So let us say initially we are initializing all weights to 0. And then this is, so first of all, we are receiving our first input. So that is because we are considering 2D space only, just to give you an example over here. So my observation is nothing but 1 minus 1. So this is my x1, x2. Now at this point of time, what is my, so this, this is denoting what? Wx, and then you are applying activation function on that. That is your sign function. So now you can see that your weight is 0 here and inputs are 1 and minus 1. And when you are adding it and applying the sign function, what are you getting? You are getting, so you get, okay, 1 or minus 1. So here you are getting answer at 1. 0 or less, let us say it is 1 or then minus 1, right? So you are getting this 1, but so your output is 1. But its actual level of this observation, the actual level is minus 1. So there is a mismatch. Actually, if your model is trained, right, if your perceptron knows it, then the perceptron for this input, it should have produced minus 1. It is producing plus 1. Right? So there is a mismatch, and because of this match, what is happening? You need to update the weight. We are talking about weight updation. So when do you need to do the weight updation? Now at this point of time, you need to do the weight updation because the actual level and the predicted level, they are not the same. Right, so when they are not the same, now this is your weight updated formula. So the weight in the previous state, right? So so what was the previous weights? They were 0, 0. Previous weights were 0, 0. Now this is your outcome, right? Minus 1. Sorry, this is label, YT. This is label. Then this is your input. Okay. Now when you just do this multiplication and addition, what are you going to get? You are going to get nothing but this minus 1 and 1. So this is the new weight, updated weight. Now let us, so for the next input, which weight you are going to take? You started with 0, 0. Now the next set of weight you got is minus 1 and 1. Now for the next set of input, you are going to take these weights. So now let us say the next point is your observation is minus 1 and 1. Right? Now when this observation is minus 1 and 1, remember that now our weight is minus 1 and 1. So just put here minus 1 and 1. So this is your weight and this is your new point, right? New input. Okay. Now again, just do the multiplication over there and summation and apply the sign function. What are you getting? You are getting here. It is positive, so you are getting here 1. Negative or 0, you are getting minus 1. It is. So when it is 1, and then see what is the actual level. Actual level is also 1. It means that everything is good, right? So no need to change the weights. You wanted the actual level to be plus 1 and your this observed level that is also giving you plus 1. So no problem, don't do anything with the weight. Just proceed. Right? So similarly here you can see that because there. So similarly again get the points and just do this weight updation till your perceptron repeated multiple times till the weights are being learned so that you are generalizing it so that now this time when you are giving it those inputs which are not seen by the perceptron, it is giving you the correct weight. So the weights are if the weights are learned with the examples and then you are giving it an unseen example and your perceptron is giving you the correct weight. So this is there. So here you can see this is your, these are your inputs, these are your weights. Now weighted sum, and this is another activation function that is sigmoid, which is one of the famous function here. So already told to you by Dr. Blake. So here you can see that simply you are just going to calculate this weighted sum and apply this sigmoid function, and that is what is your output. Right? So here you can see what is the difference between previous perceptron and this picture. If you have focused here, these are my inputs. This is weighted sum, activation function, everything is same. The only thing is what here added this yellow term. That is what we call as bias. Now, so you know why we have added activation function. Now the question comes why we are adding this bias, right? So remember that this bias term is actually allowing your shift to shift your activation function left or right regardless of your input. So always remember that this bias doesn't depend upon your input. This bias is just a number which is assigned with a particular set of input. So this is another way of showing it. So here you can see that this is nothing but this is your denoting your weighted sum and this is your activation function and that is how you are getting the output, right? So the same and here one more updation is being done. If you want to have it less later, then instead of treating bias separately, you can just have this as this xn as 1 and so weight you can give as that was the bias term, right? So you will get the same weight, right? Plus because what is happening plus b you wanted to do, right? So your last term it is 1 and its weight is b, right? So it will become plus b. So that way you can deal with bias. So this is nothing but a simple forward pass for your perceptron. So you can see this simple code is there and nothing complicated here. Now this you have already done that when you are going to add this basically it is just a linear thing. So just leave this. Okay. Now what happens when we are going to connect a bunch of perceptron together? Okay. So we talk about one perceptron. Now so this is a neural network which is nothing but a collection of connected perceptrons, right? And here you can see that if I ask you how many perceptrons are there in this neural network, so let us find out how many perceptrons are there in this neural network. Okay. So see here, this is what these are your inputs. Okay. Now this is your one perceptron, first perceptron, right? So all inputs they are connected to this. Then two perceptrons, right? Three perceptrons. So this is how you can see four perceptrons. So this is your input layer. These are your perceptrons, and then you can add it on, right? So 5, 6 like that. So here you can see that this is input layer, and when you are having multiple perceptrons, so this is also called multi-layer perceptron. And then what is happening? You can have multiple layers also. Not only this one layer, you can have multiple layers where the multiple perceptrons are there. So this layer is called hidden layer, and this layer is your output. And this perceptron, we also call it the two-layer neural network. Or sometimes, so here input layer we are not counting. So either we are calling it as two-layer neural network or one hidden layer neural network. Right? And this is your output layer, which is nothing but the decision layer, where your output, right? Decision has to be taken. Now, so here you can see that your hidden layer, this is a fully connected layer. You can see that every input is connected with every perceptron layer, right? So this is the fully connected layer, and so you can say that all pairwise neurons between layers are connected. And the same is with the output layer also. You can see that all perceptron they are connected with the other. So now if I ask you that how many neurons are there, neurons or you can say perceptrons are there, you can give me the answer, 6. Now if I ask you how many weights are there, how many weights are there? See, just see, everyone is connected with everyone. So corresponding to 1 there are 4, right? So 12 and then corresponding to 1 again there are 4. So you can see this 3 into 4 plus 4 into that is 20, right? So 20 weights we need to learn. Remember, when I'm saying just 20 weights you are supposed to learn. And so that is what is your, not only 20, yeah. So I told you about bias also. So here you can see that 4 and 2. So 4 for this and 2 for this. So you can see that 26 total parameters we need to learn for this small neural network, right? So here you can see that this performance actually give you, you are actually when you are going for deeper network, don't really improve performance. Otherwise, I mean, other than the case of the convolutional neural network, because there is, okay, I will tell you the universal approximation theorem, but before that, Let us take one more example with just one hidden layer. I don't know about time because it was so messed up. I don't know when I started. So please let me. Yeah. So again, let us take a neural network with one hidden layer. So let us say these are your features, right? So these are your features. This is one input. You can understand. This is, as remember, we were talking about xi and yi. So we're talking about this xi and yi. So this is your one input and this is your output. So let us say this is a binary class problem. So the input belong to either of the two classes. So when your input is this, then your class is this. When your input is this, then your class is this. Right? So now, and you are going to see three inputs are there. You are going to present it here, and we have just one hidden layer, and that is how the output. So when we need to train our neural network, what we need to do? See, first of all, we need to initialize the random bits. Right? Somebody was asking question also, I think, in between. So you can, the only thing is that we tell you at the end that some precaution you need to take, that what range you are taking, so that your you can learn your model easily, right? I mean, it is taking less number of steps, you can say. But in the, you will start it with a random initialization. And then you are going to present this one training pattern. So you are giving these inputs and this output, and then you are going, like I showed you in the previous example. So let us say this output should be 0, but when you are putting it here with the random weights, your output is 1. If your output is, or let us say your output is 0.8. In this example, when you are presenting these weights, then your output is 0.8. Now when but your expected output is what? Is 0. Right? So it means that there is an error. Okay. And we need to reduce this error by working on the weights, right? So you need to work with your weights via, now you already know the term backpropagation. So you are going to learn these weights so that this error may be reduced. Now you are going to present similarly what will happen. So you are going to adjust and update the weights as I showed you in the example. Then you are going to present another training pattern there to your neural network. Again, let us say this time. So you can see that this time it is learning, I mean, it has started learning slowly, it will start, your error is going to be reduced, which means that your network is going to start learning, right? So this time your error is okay, but training pattern is this, but now it was supposed to produce 1 and it is 0.3. So you can say again this error. So again you are going to update the weights and you are going to keep on presenting the training pattern, feed it to neural network, and you are repeating this process so that the error may be reduced. Is it clear? I hope this makes sense. So now when you are going for this neural network, then you need to remember one thing, that this weight adjustment process is repeated multiple times. Multiple, when we say multiple, it means that thousands and thousands of times, right? And each time you are actually using some training example, then your weights are slightly adjusted so that they are reducing the error of approximation. So with every adjustment, you wish that you are moving slowly closer to the weights which are your actual you want to learn, right? So remember that when you are doing this adjustment, it may be good for this example, right? You are putting this example, you go forward, come back. But this may not be good for other examples, right? So you just saw the output to be produced corresponding to some input. You did some adjustment, good for this one, but may not be good for the other. For the other example, this is again giving you the model, right? So what is happening? But remember that no matter what happens, right? Eventually, because you are repeating this process thousands and thousands of times, so ultimately, eventually the process of weight adjustment is going to give you good enough model for producing an effective cluster. So, and this thing, this method works well in many real applications. I decided that today I will not give you anything mathematics, right? Just I will keep it without mathematics. It's a simple discussion just to make set a stage. So now if we talk about your multi-layer perceptrons, you can see that here the input layers are there, then these are the hidden layers, this is your output layer, and or you can say that this is these y1, y2, they are the prediction of the corresponding y. Okay. Now, so there comes a theorem, universal approximation theorem, which says that any continuous function over this compact domain can be accurately approximated using a neural network with just one hidden layer, right? We don't need multiple layers. So with just one hidden layer, but of course that hidden layer may be a huge. Okay. So, but still, what we say that if layers are increasing, then the accuracy of approximation is increasing. So, because we are dealing with non-linearity and we are dealing with the complex functions in the real life, so therefore we are going to for this actually the multi-layer perceptrons were introduced. Now, if we talk about these, always remember that what do we have in this network? See, the training examples, right? At the end of the day, what do you have? Your network is learning something, and end of the day, what do you have? You have those weight metrics, right? You have that weight matrix, those bias terms. So basically, output of the behavior, the behavior of your network is actually decided by the weights, right? Because what are you doing? It's the summation, right? Multiplication and then summation. So basically multiplication by weights. So the output of the network depends upon the weights, right? So you can say that weights are the memory of the neural network and the knowledge, because these weights, they are, perceptron, they are distributed. So you can say that the knowledge is distributed across the network. And because this large number of nodes means that you are increasing storage capacity and fault tolerance also, right? So remember that how do you store new information? Let us say some new class you need to add in your input in terms of weights, right? Which we introduced in terms of weights. So here, if we can use our multi-layer perceptron for pattern classification. So in this case, you can see the output is used to distinguish between different input patterns. So let's say your digits are there, for example. So you are presenting samples of all multiple zeros, ones, twos, right? And then it is going to identify. So different output patterns, they are corresponding to a particular class of input patterns. And here, always remember that why we are using them, because linear pattern classification you just saw, and then here the networks with the hidden layers, they can be used to solve more complex problems as compared to linear network. So now here we come to the term that is called generalization. You are just doing this weight adjustment. And finally, what we want to get? We want to get that finally we have trained our model on these training samples and we got this weight matrix. And now if I put any unseen example to my network is able to classify it, right? Or my network is able to. So by proper training, a neural network may give you answer for not seeing it during training, right? But whatever data is there, you are not showing it. Unseen data, it is giving you a good performance. Then we say that it is a generalization, right? So generalization is particularly useful, right? Because noise you can't avoid, right? So how even in the presence of noise, how your model is performing. So now, as we all know that this back propagation came in 1986, and this became the popular training method for the neural network. And so what we are doing here, now you all know that what we are doing nothing, but we are working on the gradient of the current error. Remember those partial derivatives, right? We want to move towards steepest gradient, right? So we are working on the derivatives of the gradient, and that is what we are doing every time we are going to see. Remember chain rule, I will tell you more about it tomorrow class. So differentiate, again multiply, add, do differentiate, multiply, I mean so many times, right? That is how you are going to complete that chain. So when we talk about this network training, then here you can see the neural network, see sample data usually we use in batches. So that is also I will tell you. So tomorrow we'll talk about the optimization as well as regularization. So this batch data, then I'm going to forward it through the network. So you are getting the prediction, then you just whatever error is there, you are going to back propagate the error. And finally, the network weights are being updated, right? So that is there. So what does it mean? Now, so neural network, they are being trained using iterative gradient-based optimization, right? Which we will discuss tomorrow. And so what is our target? Our target is to optimize. You can take both the things, minimum or maximum, right? Gradient descent is also there, gradient ascent is also there. So whatever you wish, like minimum or maximum. So we need to actually define an objective function. Because we are going to optimize something. So you need to define an objective function that may be your cost function, that may be your loss function, whatever like these terms are being used in the text. So you are defining a loss function in terms of what? See, this function in terms of weight and mass, right? So here, then you know that what we are going to do, we are generating the error signal so that we can measure the difference between the predictions and the target values. Okay, and again, we are going to change the weights to get more accurate predictions. Right? And finally, subtracting a fraction. So the question was there on the learning rate, which I will tell you more detail tomorrow. So learning rate, so basically what we assume that we follow the, we can move towards by following small steps, which guarantees me that I will reach over. Right. So because what happens there, we need to identify this when let us say you are going from gradient descent, then you need to find out local minimum. So we need to set our learning rate in such a manner that we should not miss that. Right? Because we are setting a rate, by that rate we are moving. Now, in the movement, I should not skip my curve. So this is one of the hyperparameters in our neural network. Okay, I will tell you more about it tomorrow. So this already you know now. So you can see that multiple layers are there. And so this is called forward pass, where you are doing this Wx plus b, that is your forward pass. And then when you are taking gradient of your, then you are getting this loss, calculating loss by the predicted output and actual output. Then you are taking derivative of the loss and you are doing the math. And with this process, you can have a much deep neural network. Here you can see that not only one, but multiple hidden layers are there. So when we say theoretically, you can say that theory of approximation increases when we are increasing number of layers, but practically it is not possible. Why? Because when we are going for gradient, now there is a problem of vanishing gradients. What about if your gradient becomes zero? It means that that neuron becomes dead. Now it is not participating no more, right? It is in your process. So we need to deal with the this was also one of the problem, and so vanishing gradient problem. And then another problem is if you do not have enough data, you do not have computing power, like so many reasons are there when you go for the training of multi-layer perceptron. So I mean, so it is because since 2012 very active research is going on, several different methods are there, so that I mean basically several variants of neural network are there, so that you are getting better and better. So in one of the lecture we have kept where we will tell you after CNN, we will tell you some more models, right? Some more neural network models for this. So these are the references which I have followed, and these are the slide credits. And so open. So, I mean, you already, I think many of you have replied from my mail ID because I had this GIAN ID, but sometime I used to mail you by my personal ID also. So this is there.
Including
उसको वो कर दीजिए ना हाँ ठीक है
for this data sets that we have obtained. For starting to have data for the input data is there for that data, things don't converge. So when you apply new data, the new data is dynamically same as the data used to train. Do you see something like that? Statistically, so how we normalize it.
So that we keep it in one range basically. Then only the
So it's statistically
one minus that's all. Keep it normalized. That is what we do now. We subtract the deviation and something. By using the deviation and mean, we keep it normalized.
by lifting, you already trained it. Now, new data has a different shape. Meaning
No, what
experience-
happens that, because usually when we are talking about, when you go in the real space, then it is not like we say that every point is equally probable, but this is not like. For example, if you take the example of the image, right, your image is, let us say, 1024 cross 1024, right? So it means that 2 to the power 1024 cross 1024, these are all your data points, right? And every pixel, you can see that there are this arrangement, and every arrangement, a pixel can have, let us say, talk about binary. Okay, so every pixel may have either 0 or 1. So several combinations are possible. So on paper, several combinations are possible. But have you seen any image where which is just a random image? Nothing is visible. Like just a noise, one pixel is 0, one pixel is 1, one pixel 0, 1, like randomly. So that is one of the point from your data sample. But that point never occurs in practice. So in reality, what happens that your space looks big. But the data which we are taking from a space, that is, I mean, concentrated in some regions, right? At the closed region. It is not like the entire region is not, all points in that region is not equally problem, which we also, right? Because if you look at the image, take the example of the image, so you will not find random images. But if you talk about, I don't have that, okay, let me just a minute. Let me show you.
Take it. The cancer case tend to fall within a certain set of pattern.
Yeah, that texture information, that is what we look for. That texture, those values, because if you look at the pictures, what we have in the pictures, we have just this, just a minute. Just a minute. My God, इसकी बैटरी जाने वाली है. Now, if you look at this type of thing, this is one of the sample in the space, but this sample never works, right? In reality, no image, you will not playing with the images like this. So what happens when you model the space, that is what we say the problem with the generative AI, that we are not picking up every point from the sample. The sample space is having some density, right? So in this